Good evening, one and all present here. We are here for the live session for week 1 of the NPTEL course on urban utilities planning, water supply, sanitation, and drainage. The course instructor is Dr. Devapratim Pandit. He's an associate professor at the Department of Architecture and Regional Planning, IIT Kharagpur. I am Monica S. I am a research scholar at the same department. And one second. So today's session essentially will be a discussion on a few assignment questions of the previous run of the course. So this is the second run of the course. You will be, if you noticed in your interface, you would have gotten an assignment for week 1. So there were a bunch of questions there that you will have to answer, and it will be graded for your evaluation for the issue of certification. However, currently in this session, we will be discussing a few questions from the previous run of the course, which are not really part of the current graded assignments. So there are two ways of interacting in this session. One is this live session, which is going to happen every Monday from 7 p.m. to 8 p.m. For the next 12 weeks. So you can, at the end of every question, I will prompt you as to whether you have any doubts, whether you have queries. You can raise your hand, and then once I allow you to ask the question, you can unmute and then raise your query. So this will be only regarding the question that I've just explained. And then if you're not uncomfortable with a live questioning, you can also post the questions in the chat box. The other major means of discussion would be the discussion forum, where any questions related to the live sessions will be answered by me. And questions will either be addressed in the forum or in the next week's live session. Within this interactive session, we'll also have an interaction at the end of the class where you can ask me general queries, either pertaining to the NPTEL course that we are looking at, urban utilities planning, or any other general query that you think might be pertinent for your understanding of this course. I would also like to bring to your attention that I'm a PMRF scholar. I have been recruited under the Prime Minister's Research Fellowship. So, any minor or major queries regarding that will also be attended to, but I would still request you to stick to the course. So, a small recap of week 1 lectures. First lecture was on issues in urban planning in water supply, in drainage and sanitation. Lecture 2 and 3 were dealing with planning strategies as to how do we go about it. It's sort of an initiation into how does planning happen in these domains, in the infrastructure domains of water supply, sanitation and drainage. So if you notice, general planning is a very broad area. It's very generic in its approach, and you have multiple comprehensive issues that you need to be taking into consideration. However, infrastructure planning is very niche at its core, and it's very technical at that. So these are some of the planning strategies that we looked at. For example, population forecasting and how do we go about funding, what is the design process of infrastructure. These are things that we looked at in order to get an initiation as to how is the process of planning when it comes to urban utilities. Lecture 4 had a basic introduction on these three urban utilities as well, and then we delved a little into water sensitive urban planning. So today's live session will be a major focus on lecture 2 planning strategies. Particularly, we'll be looking at population projections. We'll be looking at a couple of numerical questions. These, I hope, will help you answer questions that are there in your current graded assignment as well. So they won't be the same questions, of course. We are going to look at similar problems. I will be introducing a very basic problem in the beginning as to how to go about your estimation, and then we will be looking at what more is there to it. We'll also be looking at a few theoretical questions that were part of the previous graded assignment. So let's delve into the population forecasting methods. For those of you who have joined late, this session is going to focus on questions from the previous round of the course, which are not part of the current graded assignments. However, they will help you attempt the graded assignment in a more informed way. So essentially, what we are looking at are trend extrapolation methods of evaluating population. So what do? We look at the trend of population change in the past and then use that to sort of project into the future as to what the population could be. But why are we doing this? So whenever take a water supply network, we might be looking at the scenario currently in a city and we might be designing the network for the current population. But if you have noticed in the lectures as well, there is something called a design period. Infrastructure is a very solid element, is a very durable element which stays on for years, usually a few decades. And it so happens that most infrastructure actually stays on for more than their design period. Like the standard design period, if you've noticed, for most infrastructure under water supply, sanitation, and drainage is 30 years. However, again, if you've lived in any of the major or even some of the second tier cities in India, you will notice that these infrastructure are not really taken down at the end of 30 years, right? So they have a very long period of time that they exist for. So say you plan for something as short term as the current population, what we will end up doing is we might end up designing infrastructure that is heavily uh, falling short of the requirements of the day when it comes to say 5 years down the lane. Okay, maybe 5 years down the lane is not so much of an issue, but what about 15 years down the lane or 20 years down the lane, 30 years down the lane? The infrastructure is going to be so constrained that it is either A, going to limit the growth of the city itself from attaining its full potential, or it will end up causing problems in terms of operation and maintenance, where people end up moving into the city no matter what, or into that area of the city no matter what, and then the infrastructure is overstrained. So the trends that we are looking at right now, there are a few pros and cons. The pros are that you don't need much of data requirement, and there is not much expertise required to delve into the current methods that we are going to look at, the two methods that we are going to look at today. However, the cons are that the inferences are at the aggregate level. What does that mean? So when you draw an inference for the entire city, it doesn't mean that those inferences will be valid for a smaller area within the city, say a ward or a small sector. Some cities are divided into sectors, or a neighborhood. No. So these methods apply for a city scale or a larger scale that you are taking into consideration. Uh, that's the basic con against such methods. That being said, it so happens that we have much more advanced population projection methods that overcome the shortcomings of these methods. So we are essentially initiating you into population forecasting. However, for somebody who's very interested in knowing all the methods, there are regression based methods, there is cohort analysis, and in fact, there are master's programs provided in demographic analysis in the country. It can go as deep as that. There are probably people doing research on how best to fit these population projection methods. But we're going to look at a couple of them that will initiate us into the topic. So there are three terms that you really need to know when it comes to population forecasting. One is the base year, which is the year from which you have data for. So, in the case of India, our data is primarily going to be from the Census of India, and Census of India are decadal surveys of population. So, base year is the first year for which you have data available for your area of query. Launch year is the last year for which we have data. and the target year is the year for which you're planning to find out the population for. So in case of say our requirement, we might need it for like 30 years down the lane. So the first method that was introduced in the lecture was the arithmetic increase method. So it is based on the assumption that the population is increasing at a constant rate. So the rate of change of population with time will be constant. So all this will make sense when we start working out the problem. So essentially, this is the formula that we'll be using to compute the future population. PT is equal to P0 plus MT, where dP by dt is essentially the constant m, right? So is the rate of population change, which is m, population growth rate. PT is population at time t, so this PT is what we are trying to calculate. We are trying to figure out the population in a future year. So say currently we have population data till 2011. Say you want to project for 2041, 51. So then you have P0 is the initial population. So what is the latest data that you have for that particular area? So what we saw as launch year, and T will be the time in decades. So this time in decades will be calculated relative to P0. So how far is PT from P0 is the question. So let's delve into the question so that we can get a better understanding. This was a question from the previous year's assignment. Again, it is available for download from your NPTEL interface. Population of a district based on census data is given as follows. So we have data from 91, 2001 and 2011. What will be the forecasted population for 2031 based on the arithmetic increase method? So instead of delving into such big numbers, let's one second. Okay, also I could have done this. Okay, so in here in this question, this will be the base year. So this is the first year for which we have data, 1991. 2011 will be the launch year. So that is the latest data available, like the last data that you have, the recent most data that you have. And 2031 would be your target year. So what are you planning to evaluate the population for? So these are the 3 years uh, that we have. So for those of you who are joining late, as well as for everybody else's reference, the videos of this lecture will be available and circulated later as well. So you can refer to them later. So let's take a small example to understand the arithmetic increase method. Okay, Rambak, I will give you a small introduction and then we'll go further. Okay, so reeling back slightly for those who have joined very late, we are going to be looking at two sets of questions. One is theoretical questions, which will come in the second half of the lecture if we have time. But the first half of the lecture is going to be on a couple of population forecasting methods. So you have weekly assignments in your NPTEL course that you need to submit, and it's part of your graded assignments. You will be graded for those assignments. These interaction sessions and the questions that I'm taking up are to enable you to calculate the answers for the same, or rather figure out the answers for the same. So I started with how pros and cons are just theoretical. So there are 3 years that are there. One is the base year, launch year, and target year. So the base year is essentially when you have a bunch of data and you want to forecast population. Base year is the first year that you have data for from, say, Census of India. Launch year is the latest year or the recent most year that you have data for. And the target year is the year for which you want to calculate your population. You want to project the population for. So let's look into a small problem. Let's not look at the big numbers. So say you have a small area, and we have data from 1980 to 2010, say 8,000, 12,000, 17,000, and 22,500. So how do we go about this? What we do first is we estimate something called increase in population. So, how much is the population increasing every year? So, when say 1980 it was 8,000, and then 1990 it became 12,000. How much was the increase in population in that decade? So then we compute that. So that's 4,000, and then for each decade we compute the number. So essentially we'll get three of such estimates, right? So it'll be 17,000 minus 12,000 will be 5,000. 500 minus 17,000 will be 5,500. So then we estimate the total increase in population, which is the sum of all these numbers. So 4,000 plus 5,000 plus 5,500. We also find out how many decades is this sum for. So then we realize 1980 to 90, 90 to 2000, and then 2000 to 2010. So we have 3 decades that population that we have considered. So the average increase in population for this period, for the data that we have for the particular area, is 4,833. Remember, in population forecasting, we always round the numbers. I mean, it doesn't make sense when you are estimating the population of an entire area to say something like zero point 0.5. We cannot have zero point 0.5 human beings, right? So, and it's an approximate estimate at the end of the day. Different methods will give you different numbers. So, might as well round it off. So here it was for 4833.33 if I'm not wrong, and then we round it off. So from the formula, what we do is, so the formula is Pt is equal to P0 plus Mt. So right, so which year are we going to project the population for? Say we are looking at 2020, which is 1 decade from the launch year, right? So our launch year is 2010. That is the latest data that we have. So then we calculate this T, which is time indicates. Time indicates is not just, it's with reference to the initial population or the launch year that we have, right? So whenever you take a P0 and then you calculate T is always the decadal difference between P0 and PT, right? So in this case, we have 1 decade difference. So 2010 to 2020 is 10 years away. So that will be 1. And then the population will be employing this formula. So we take the initial population, which is 22,500, and then we multiply 4833 with this. So M is 4833, which is the average increase in population over the years, and we multiply T, the time indicates, from the initial population, and therefore we get this number. So let me work this out again in Excel for you. So we have this 8,000, 12,000, 17,000, and 22,500 as our numbers that we already know. So we are going to try to find out the numbers for 2020 and 2030. So we'll start filling in. So 8,000, 12,000, 17,000, and 22,500. Right. So what is the increase in population here? That will be 12,000 minus 8,000. So right, you get 4,000, and then here the increase in population will be 17,000 minus 12,000. So I've done all this in Excel, you have noticed, and then the last difference will be 22,500 minus 17,000. So these are the 3 increases in population that we get, and the total increase in population is just sum of these 3. So I've added these 3 numbers to get the total increase in population. So then we figure out how many decades is this for. So what is T here? So we have 3 decades data. So 1980 to 2010 is essentially 3 decades. So then the average increase will be 14,500 divided by, and you can see that I've rounded off the number. So this is our M value. So for the year 2020, how many decades is it far away from 2010, our launch year? It will be 1. So the increase in population is 27,333. And then 2030 is 2 years away from our launch year. So then the population will be 32,166. So going back to our question that was raised here. So this was the question as part of the previous assignment. These are the population numbers given. So let's put those numbers in our template. So 1991 was 80,500, 2001 was 5,35,000, and 2011 was, sorry, there is some issue in the number. Okay, so it is 10,36,000. Right? So let's, what we do is first take the population. Right. So this will be our initial population or launch year population. The increase in population of, obviously for the first year you have nothing because there is no data before the base year. Then second will be population for 2001 minus population for 1991. Third one will be population for 2011 minus 2000. So this is the total increase in population, and we have 2 decades of data. So this is the average increase in population, which is the M value. Right. So now calculating the time in decades. So with respect to launch year, 2021 is 1 decade away. So here, if you notice, this is P0. P0 is our initial population. So that will be population of 2011. And then plus M into T. So M here is average increase and T is the time period decadal difference. So again, so when you calculate that for 2 years, this is the number that we're getting. So if you look at the options that are available, this will be the answer that we get. All right. So, any questions on the arithmetic increase method? Please raise your hand and I will call out names. Please bear with me if it is a little basic because we have a huge crowd that we are catering to. With the time period, which part of the time period? Can you unmute yourself so that I can explain? Or is it difficult? Yeah.
No, ma'am. Am I audible?
Yes, you are audible. Please.
Ma'am, the part where you have taken first year and then the second year, ma'am, can you please explain that part kindly?
Okay, I will share my screen and then I'll continue.
Okay.
So if you notice here, so you're talking about this 1 and 2, right?
Yes, ma'am. This 1 and 2. Yeah.
So forget this, forget this. So until here you've understood, right? The M calculation.
Yes, ma'am. The M calculation was
So
understood.
when you're calculating this formula, T, where what you have here, so this is for the formula is time in decades. It is the difference between the year that you are evaluating for, which is 2021, that and P0. P0 is the last year that we have data for. So 2021 minus 2011 is 10 years ka difference. However, we are doing it in terms of number of decades. So we are doing a decadal calculation, right? So we will take it as 1. So 1 decade is 10 years. So the gap between 2011 and 2021 is 1 decade, and therefore you got 1. 2011 to 2031 is 2 decades, therefore you got 2. So when we are calculating the increasing in population, so that will be equal to T0, so that is 2011 population plus m into t. If you see the formula, pt is equal to p0 plus m into t. So m is the average increase in population per year. So it will be this value into t, the number that we have given calculated as the difference between these two decades. So that will be this. So for the second 2031, it will be P0 again 2011 ka value plus M into T. T is 2 this time because the difference is 2 decades. So you can see the answer it's 19 lakhs 91,500. Am I? Is it clear now?
Yes, ma'am. Understood it clearly now. Thank you, ma'am.
You're welcome. Anybody else? Any other questions? Otherwise, we'll go to the next. All right, we'll move on to the next question. We can take any more queries in the end as well. So, I'm not going to really solve a problem with the geometric increase method because again it was not part of the assignment. So, but this is a basic introduction to the geometric increase method. In case of the geometric increase method, the formula is Pt is equal to P0 into 1 plus m to the power t. So here what we do is we calculate the population increase just like in arithmetic increase method. So we just find out 2001 ka population minus 1991 ka population and then 2011 ka population minus 2001 ka population. So we after we find out these increases, what we do is in order to calculate this m, we take the percentage increase. So how do we take the percentage increase? Here it is 83 lakhs 89,793 divided by what is the year before that. So 8 lakhs 20,995 will give you into 100 of course will give you 10.22%, right? And then sorry, it's actually not calculated over 100. The increase is quite tremendous. So you just take this value divided by 82,000, sorry, 8,20,995 and you get 10.22. The second increase, again, you take the value of the increase divided by 2001, the previous year's population, and then you get 0.19. So how do you calculate this m value? You multiply, you take a geometric mean of these two. The geometric mean is calculated by multiplying these two values. So 10.22 into 0.19 and then taking a square root of it. So 1.412 will be your geometric mean. And then you add it in the formula. So 820995 is the P0 initial population. So here, in case of geometric increase method, we take the first year as the initial population, and then you multiply it with 1.412, and then you get a cube. So there are two methods of doing this. When you take 1991 as the initial population, 3 is the time period. Why? Because 2021 is 3 decades away. However, if you take 2011 as the initial population in this formula, you just have to give it as 1. So the difference between time periods is 1, right? So whenever you take P0 as 2011, it's always better to take the latest year available for calculation. So when you take P0, make sure T is calculated as the decadal time difference between PT and P0, right? Moving on to the incremental increase method, we'll be looking at a problem for this as well. So incremental increase method is sort of a trade-off between geometric method and geometric increase method and arithmetic increase method. First, we take the average of the increase in the population by arithmetic method, just like differences between populations, and then we take an average of the net incremental increase. So again, things are going to sound very in the air if we just look at formula. I'm going to explain it with an example. So here, this is the question from the previous run of the course. So for the given population data, what is the forecast population for 2031 based on the incremental increase method? So we have data for 5 years. So instead of taking this data, let me again take a basic data sheet. So what we have done here is we have 8,000, 12,000, 17,000, and 22,500, just like our first example. And we're going to use the incremental increase method now. So firstly, just like how we calculated an arithmetic increase, we calculate this increase in population. So we calculate this increase in population. It will be 12,000 minus 8,000 is 4,000, and etc. So 17,000 minus 12,000 is 5,000, and 22,500 minus 17,000 is 5,500. Then you calculate an increase of the increase. So how much is this increment changing? So from 4,000, so from 1980 to 1990, population increased by 4,000, and then 1990 to 2000, population increased by 5,000. So how much is this increase? So that will be 5,000 minus 4,000, and that will be 1,000. So again, in the second increment, you have 5,500 minus 5,000 will be 500. So what we are calculating here is how much is the increase increasing, like how much is the increase changing by. So then we take a sum of these two numbers, and then we again, so this time we don't divide by the total number of decades, we divide by the total number of increments. So how many increments do we have? So we are basically finding an average, right? So we have two numbers and we are finding an average for the two numbers, so we are dividing it by 2. Right. So then when we are calculating, say for the year 2020, so the formula has three components, right? P0, T into M, and then T into T plus 1 by 2 into K. Right. So what is P0? P0 is the initial population you're considering. So what are we considering our initial population as? The latest number that we have, 2010. And then pt is population at time t. So which year are we estimating the population for as pt? So then the first component of the formula is this initial population. Second component is t into m. T into m. So here again, time in decades is just like an arithmetic method. The time in decades is the year that you are projecting for minus the year that you are taking as P0, the initial population. How much is the decadal difference? And M, we just like we calculated in arithmetic. So M will be calculated as sum of this total increase in population. We find the total and then we divide it by 3, right? So the average of this increase in population is M. That will be your second component. So T into M we calculate, and then the third component is T into T plus 1 by 2 into K. So what is K here? K is the rate of change and increase for each decade. Basically the average incremental increase. So this increase of increase, what is the average number that we have? That is 750. So let's do this from the scratch so that will be easier for you. So we have four numbers here. So what is the increase in population? First year we obviously don't have any other number before. Increase in population here will be 12,000 minus 8,000. Increase in population here will be 17,000 minus 12,000. And increase in population here will be 22,500 minus 17,000. So we have the increase in population. Then we take the sum of these. So I'm using the auto sum feature in Excel. Sum of these. And for average, how many decades difference? 3. So we calculate the average as 14,500 divided by 3. So this will be our M value, right? So then we find out the next column, which is incremental increase. So here we have 5,000 minus 4,000, 5,000 minus 4,000, and we also have 5,500 minus 5,000. So that will be your incremental increase between the two. So then again we find out how many increments do we have? 2 increments. So that will be 1,800 by 2. So this will be your average incremental increase. Alternatively, you can also use the average function in Excel. I'm just giving you extra information now. The average of these two numbers, 7, right? So now we calculate the components for this formula. What is the first component is initial population. We have 22,500. Then the second component is T into M. So we need T for that. So 2020 is one decade away from our initial population, 2010. So it's one. And the T into M is essentially 1 into 4833. So that was our average increase in population. We also have the third component will be T into T plus 1 by 2 into K. So let's calculate. Uh, K is this number and T is our time and decay. So that will be T into uh, sorry T into T plus 1. I'm giving back brackets even though there is a sequence to Excel working on it. I'm making it clear here. Divided by 2. So the whole of this multiplied by K. K is our average incremental increase, which is 7. So this is the third component. So this will be our population. So T0, which is P0, plus T into M. T into M plus the third component, T into T plus 1 by 2 into K. So this will be the estimated population. Again, so if I fix these numbers, so in Excel, whenever you want to fix, when you drag a formula, what happens is, I hope you know this, but I'm repeating for the sake of those who don't know. When you drag a formula, the formula gets applied in the next cell also. But what happens is usually the cells will move. So let me demonstrate. So what happens is usually both the cells will move down one when you drag by one. So in order to fix this, we can use F4 or make it into $E $16. So this cell will be fixed. Then you drag this value. Then you will have the T part will be moving down, whereas your M is fixed here. So similarly, you calculate this and the population. Population again. This will be the population. So these 2 years will have these populations. So let us work out the question that was given here in the previous run. So I've taken the numbers here. So when you put the numbers in, these are the values that you get. So number of increments has become 3 now. So and the number of decades is 4. So this is our answer. If you continue all the steps, you'll get this answer. So this is our answer for the problem. So alternatively, in the answer key that has been given to you, you can see that P0 has been taken as 1971, the initial population. Then your T will change, but it will essentially give you the same answer. So it's not going to be different, at least not drastically. So we don't have to worry about it. So any questions regarding this problem? Right. I hope that was clear. Any future questions you can post in the discussion forum or anywhere else. So let's look at a few theoretical questions. So are there any other general questions that you have regarding the lectures that were taken? Because we have around 17 minutes left. If there are no other general questions, we can go discuss some theoretical questions. Are there any general questions or queries that you had? I hope you went through the lectures from the week. You can raise your hand and I'll allow you to ask the question. Or if you are yet to look at the lectures, you can go ahead, look at them. You can raise the questions in the next week class or in the discussion forum as well. Please feel free to reach out to me on any question, even if it is slightly tangential to the course, but if you want more understanding, we can deal with them here. And this session could, right, yes, please go ahead, Chamba.
Ma'am, I had one doubt.
Yes,
Ma'am, suppose we face any problem during solving those assignment problems.
right.
So in that case, shall we create a WhatsApp group? Otherwise, how will we connect you?
You can post in the discussion forum. I hope it's visible in the NPTEL interface.
Okay, okay, ma'am.
So you
Okay.
can post in the discussion forum. The thing about, I would actually rather give you my email ID. But the thing is, it just happens to get lost in the process. So I might not check my mail all the time. But the discussion forum is something that I'm obligated to check. So what we
Okay,
can
ma'am.
do is, I will give you my personal mail ID also. You can feel free to reach out to me. I don't mind at all. Whenever I'm free, I can get back to you. Uh, yeah, will that work?
Yes, ma'am. Sure.
Okay, so I'm posting it in chat here. So which method is more accurate or how to decide the method to calculate? Okay, so Trambak, your query is done, I hope. So calculate future population density. So Rahul, actually speaking, we have a lot many more methods. These are not the only methods. We have linear regression based methods and methods that, so if you've noticed in the lecture, gender and smaller groups are not taken care of in this cohort. What we usually do in planning is we take decisions that are ad hoc. For example, I think we had an exercise in my master's at IIT Kharagpur. We had to project the population for a very small city, and the population was going everywhere. Like, we realized we cannot use any of the methods, and we actually came up with something. We used an economic model that also Sir talks about. So there are multiple considerations. I will be very honest with you. What happens usually is you justify your decision. So if you think, for example, the city is going to say grow in a similar direction or in the same direction, you can use arithmetic projection. Or if you are using a regression model, you can go check up regression models of population projection. I can also share some good reads or materials on it. Probably in the next class I'll post it. So in those projections, so the graph will essentially be linear. You can also see it in Sir's lecture how he talks about. Is my screen visible? No, right? Okay, I'm not sure. One second, I'll show you the. Okay, so I hope my screen is visible. So if you see here, these are the three methods for the same problem. The lowermost line is arithmetic increase. So you see how the city is not growing very much. And the geometric increase is if the city is going to suddenly grow very bombastically. Say you are having a very major employment opportunity or an industrial um, SEZ or an industrial settlement being planned in the city, then population will increase because of migration. Or in case of US cities, if you see, a lot of these older industrial cities are dying out now, so there will be a population decrease. So you can't use, and there is sometimes a tremendous population decrease. Or there is a disaster and then like a major disaster and then there is a population decrease. So all of these have to be taken into consideration. Incremental increase is somewhere between these two, geometric and arithmetic increase, but it is a case by case basis. You will know only based on which city you are selecting. Uh, there is no commonly used method either. Actually, if you go back into how many population methods are there, there are a bunch of, there are like 10, 12 methods that I myself know. So for the purposes of this course, you can use one of these methods and you can just justify saying, okay, you know what, I think the city will not grow much, so it should be fine. I hope that answers your question, right? So, also, just to bring to your notice, so there are measures of comparing outputs from different population projection methods. It's very, I need to take a lot of background for that, so I'm not going to discuss them here. But I will show you briefly if you are interested in it. Any other questions in the meantime? So I'm sharing my screen. So if you remember, I spoke about linear regression based population methods. So this was a class on those population methods. So we have logistic projection, linear projection, geometric projection, all these in there. So these are the four methods: linear, geometric, parabolic, and logistic. So these methods are not taught you here, and it is not necessary to be known for this course. But for general knowledge, if you notice, there are multiple methods of, so you can either visually look at the graph and then see which is most appropriate. There are measures like coefficient of relative variation or mean absolute percentage error. So then you calculate these values. So the values are here. Then you calculate the values from these values. You can figure out, okay, this is a good method to, which should I select, etc. So that's how we work for more complicated or technical projections. I hope that answers your question. Right. Okay, so we'll quickly go through a few theoretical questions. With theoretical questions, what I'll do is I will show you where it is there in the lecture. All of them are covered in the lecture. All the questions are from your lecture material. Please go through the lecture. But I'm going to show you where the answers are for a few of the theoretical questions. So, the question two in the previous run. So, which among the following causes a decline in groundwater level? A. Uncontrolled and illegal extraction. B. Rapid urbanization. C. Construction of concrete surfaces. And D. Lack of enough water recharge structures. So, if you notice, I think uncontrolled and illegal extraction will essentially lead to overexploitation of water. Rapid urbanization, again, because more number of people are consuming water from the same amount of, like, same patch of land, or they will end up taking up water from the same aquifer. If you remember, aquifer is a porous bed of rock that contains water, so that is where we derive groundwater from. So yeah, I know. I'll come back to that. I'll just finish this question and we'll come back to that. So, sorry, wrong presentation. So, construction of concrete surfaces will inhibit the recharge of water. So, what will happen is all of the water will end up flowing through to another water body, and then the recharge potential will reduce, and lack of enough recharge water structures. So it's not enough that you have soil everywhere. Soil will still permit flow of water. So we will need some. So naturally, previously we had lakes and such water bodies, that ponds and lakes that sort of acted as these recharge structures. Right now we have infiltration wells and other wells that are, or recharge pits that we create for the purpose. So if you notice, it's there in under urban utilities planning issues. So this is the first lecture, and these are the options that have been given. So coming back to Trump's comment, yes, all of them seem relevant. That's why it's a very case to case. What are you going to use the projection for? Right. There is also something that I should mention. So some might think, okay, why do we have to project population? I will assume a very huge number so that the safety margin is very high. Say population projection gives me 1 lakh from say arithmetic increase method or some method, and most methods are giving me 1 lakh, and I decide on 1 lakh. But then I think, no, I want to design such a beautiful system that I create something for 2 lakhs population, and say the current population of the city is 50,000. The problem is we cannot over design structures as well. It's not just a matter of cost or taking up land or wastage of resources, but there are certain mechanisms within the infrastructure that will fail if we overestimate the population as well. For example, there is something called self-cleansing velocity. You will learn about this as teachers in the future lectures. So we need a certain minimum amount of water to flow through the pipes so that the pipe gets cleaned, right? Like so that nothing stays or nothing stagnates. All the solid particles don't say, stick on the surface of the pipe. The issue with such stagnation is beyond a point they will solidify, and then the movement of water will be inhibited, and the effective surface area, like the cross section of the pipe, will be reduced, and the whole efficiency of the system will go down. So it's not like we can go ahead and design over design as well. So we will look at the case. If you, as planners, as we go through multiple subjects, and then we start taking certain decisions based on few factors coming in. As I said, is there going to be more development, or are we expecting that there is going to be a boom in the city, or are we expecting that it's been a city that has been stable for 10 years? Why is it, sorry, 10 decades? Why is it going to like suddenly increase? We don't think it is going to increase. So then in that case, it will not increase. It is a very subjective decision. In fact, the easiest decision that we use is graphical method. Again, I think you can go check out Professor Pandit's lecture that is mentioned in the current course as well. There is an urban land use and transportation planning course. There he has done detailed demographic analysis lectures. So there as well, he talks about how we can compare graphs and make an approximate estimation. Population forecasting is very approximate at the end of the day, right? So we'll go back to a few more questions. Yes, go ahead, Swami.
Yes, ma'am. So as the course deals with water sanitation hygiene, ma'am, so groundwater is definitely a part of it. So
Yes.
in future, if we expect more of population boom, and as we know that in case of cities like Kolkata, then Bangalore, Chennai, all those metropolis cities. So in that case, how is it possible that we construct high rises as well, and we keep the groundwater also above the adequate groundwater can be in a balanced position. So
Hmm.
how can this ecosystem be balanced?
So there are quite a few measures to do this. One of the first things that we do is stop access to groundwater. So, for example, in my home, I am from Chennai. Currently, they've asked us to pay 10,000 rupees per month if we want to access groundwater. So what happens is most people will opt out of it. It is a matter of implementation. I agree. People might still, go ahead and say, okay, how are they going to find out? But with regular inspection, we can actually block access to groundwater, and there'll be special permits saying, okay, these uses or these buildings can use groundwater. The other thing is metering. So even with groundwater use, what we can do is we can attach a meter, water consumption meter. So what most cities are going for is centralized supply of water, so the municipal supply of water, wherein they can actually account for. So they do the groundwater extraction, or they tap into alternate resources and everything, but they manage water supply, which is where we are trying to. Most cities are trying to push into metered connections and municipal connections instead of people using groundwater motor pumps to take out groundwater, right? Yeah. So as you go on, you can. There are a few innovative measures are also coming up. So it's not like it doesn't have to be a particular, uh, method. Again, planning is a very case-based thing. So context matters. What might be applicable in the US will not go in India, and what might be actually acceptable in India, the higher probability that they will reject us. So reject that method. They might bring in more human rights considerations. In India, we are a little more laid back. I'm not saying we are very laid back, but we do walk into gray areas. So there are also advanced modeling uh, methods that have come up uh, with regard to demand forecasting and stuff. We will also, yeah, we can assess the problem using GIS. We can assess the problem using GIS as well as, in fact, satellite imagery. There are means of estimating the level of groundwater. So we can monitor how much groundwater is available, where is it being overexploited, how much is it changing, and then we can take selective measures in those areas instead of putting a blanket rule. Yes. All right. I think we are done for the session, unfortunately. So the answers for the questions that I was, the theoretical questions I was about to discuss are also given in the NPTEL interface. You can go through them for further understanding. Again, please note that all the answers are available in the lectures. If you want any other additional inputs, you can always reach out to me. I think I've posted my email ID here as well. It's better if it is there in the discussion forum. I hope the session was useful. Thank you one and all for coming, attending the session. Thank you. In case you have any feedback or you think it's too basic or you want things to be more advanced, you can reach out to me. I will try to accommodate. Thank you for joining us today. Thank you.